So welcome to this session. This is a live NPTEL session for the course Principles of Signal Estimation for MIMO OFDM Wireless Communications. And so today we are going to see the contents of week 2. And as we have received a doubt regarding week 1, so I'll take that first and then we'll proceed to week 2. Okay, just a minute. So what happens is that so we have this estimate, right? So we have the estimate which is Gaussian distributed. Just as H and yeah. Right. So we have this estimate H. So the error, yeah. So we have H hat is Gaussian distributed. Okay, as H and sigma square over n. So now our first objective is to convert this Gaussian into a unit Gaussian. So what is a unit Gaussian? So a unit Gaussian is if it has a mean 0 and variance 1. Okay. So just go down. Okay. So we have this as this. Okay. So we want to convert it into a unit Gaussian having mean 0 and variance 1. So what do we do? So first, to remove the mean from this, what is the mean? We have the mean, that is expectation of H hat is H, right? So we want to remove the mean, right? So H hat minus H. Now this random variable is again Gaussian distributed and now it is having 0 mean, but the variance is still sigma square over n. Okay. And now if you want to further, now we have to remove the variance component, right? So this is H hat minus H divided by the standard deviation. Okay, so standard deviation is root of variance. Yeah, so the standard deviation is root of variance. Okay. So now this which we have, this random variable is now a 0 mean and unit variance random variable. Okay, so in the numericals, we have probability, say some x less than equal to H hat minus H. So it is this kind of a problem, right? So the only problem is when we have this H hat minus H. So the random variable does not have any mean component, but it is still having the variance. So to remove the variance, we have to divide completely with standard deviation. Okay, so we divide it by root of sigma square over n, H hat minus H over root of sigma square over n, x by root of sigma square over n. So why do we have to do this, right? Why do we have to convert it into unit Gaussian? So that we can now solve this by using the Q function, because the Q function is applicable to symmetric Gaussians and the exact Q function is applicable to unit Gaussians. So you can easily solve this by using since we have now converted this random variable h hat minus h over root of sigma square over n. So now unit Gaussian can be easily applied to it. Yes, you had someone is raising hand. You can please go ahead.
Yeah. I'm not able to see the notepad if you're sharing.
Oh, is no one able to see the notepad? Can others please reply?
Notepad is visible, sir.
Visible, right? Okay, ma'am, I think it is problem in your end. You can
Okay.
possibly log out and come in again. Right.
Sure.
Yeah. So what will happen is this will be q of minus x over root sigma square over n minus q of x over root sigma square by n. And since we have this property that q of minus x is 1 minus q of x, so we'll use that. So this becomes 1 minus 2 times q of root sigma square over n. Okay, so I think Ilaya sir asked this question. So is this fine, sir?
Yes, sir. I understand. Thanks.
Okay, so I think in week 2 also we have one such problem. So when we'll discuss that problem, I think it should be more clearer. So this is the concept. Okay. Right. So so far what we are doing is that we have this constant signal which we assume to which is being transmitted at the transmitter end, right? So we have some transmitter end and some constant signal is being transmitted, and we receive some random fluctuations at the receiver, and we assume that we know the distribution of the white noise. So the distribution of V, which is 0 comma sigma square, is known, right? So we assume that we have this information, and then what we do is this analog value which we get at the receiver, we sample it, right? We sample it out. We get some samples. We take n number of samples, y1, y2, and so on yn, and these n samples now we have, and we are trying to estimate what was the parameter which was transmitted, right? You can consider that, say, 5 volt was being transmitted, and say you are receiving some fluctuations, so you can receive 4.6, 5.3, something, right? And now you have these values at hand, and you want to estimate what was the transmit symbol which was being transmitted. So in the week 1, the entire analysis was a real analysis, right? So this signal which was transmitted was a real signal, and what you were receiving, that was real. It was assumed that the white Gaussian noise is also being sampled as real only. So now we are going to extend our analysis to complex parameters, and we will see what changes do we see in the analysis. So now we have this H which is being transmitted. So it is now having two components. One is the real component and one is the imaginary component. So we have H is HR plus J times HI. Okay. So H is complex by nature. J is root of -1, which is also called iota. And our signal model is Yk is H plus Vk. This is the standard signal model which we are considering from previous week, and we carry forward the analysis. So since my H is having real and imaginary, so now what will happen is that the Y will also have some real and imaginary component. And if we assume that, say, the Gaussian noise is also having some real and imaginary component, then in that case, we have a complex noise and we have a complex observation, right? In addition to the complex signal which was being transmitted. So now we have, say, all the real components are denoted as R, and all the imaginary components are denoted by I, right? So you have y real at instant k. So this you should note that k denotes your time instant. So this entire analysis we are again seeing for only one sample at any one time instant, and then we will extend it to multiple time instants. So for a single time instant, y are so we broke it. Now to solve this analysis and to simplify the process, we will split the complex signal which we are receiving into the real and imaginary parts, right? So now for the real part, we have all yr1 to yrn, which is hr plus vr1. This is at the first time instant. Similarly, if we talk about a general case, say yrk, it will be hr plus some VR of k, right? So we should still note that HR and HI, they are still time invariant. Okay. So they are still considered to be constant over time. They are not varying over time, and all the VKs, are IID Gaussian. And in the last week, I had explained IID, so independent and identical. Okay. I'll explain again. So we have independence and we have identical. So what is the meaning of independence? So independence means that the joint PDF is product of individual PDFs. Okay, and identical means that the correlation of any two, say you have V1 and V2, and it is 0. So identical and independence. Okay. So since so this analysis will be done as we did in the previous week, and if you remember that the estimate comes out to be the sample mean itself. So what we are saying, so if I again go back to this diagram, so so some constant signal is being transmitted. You receive some random fluctuations. You sample those fluctuations, and these samples is what you have at your hand. And if you take the mean of these samples, right? If you take the mean of these samples, then this mean, so this red dotted line which is there, so this mean is the average of which is the h hat, right? So which is your estimate. So for the real part, if we split this complex part into the real part and the imaginary part, then we see that the estimate is the real part itself. Similarly, on similar lines for the imaginary part, if we take yi to yn, similarly hi plus vi1 or hi plus vin, such that all these vi case are IID Gaussian, then all the yins will also be IID Gaussian, and we can again apply the maximum log likelihood estimator, which we saw in week 1, and it will again result in hi hat is 1 over n summation of the samples, imaginary samples, right? Okay, so the net estimate will be h hat r plus it should be j times hi hat. So we have the real part plus the imaginary part. Okay, right. Now we assume that the noise samples of the real and imaginary part are both IID and Gaussian. Okay, so if we take each sample which comes from a Gaussian distribution having mean 0 and variance of sigma square by 2. Right. So what we are saying that we have to so what we are saying is that all VRKs come from a Gaussian distribution having mean 0 and variance sigma square by 2. Similarly, all imaginary samples come from a Gaussian having mean 0 and a variance sigma square by 2. Okay. So we have the first property. So expectation of the real samples along with imaginary samples is the individual product of both of them. Okay, and this comes out to be 0. Okay, why is this 0? Because it is given that both of them have 0 mean. Okay, so we see that the real and imaginary samples are uncorrelated. So one very important property which you should note is that if two random variables x and y, if they are independent, then they will be uncorrelated. But if any two random variables are uncorrelated, then it does not guarantee independence. So this is a very important property which you should note, that independence means uncorrelatedness, but the reverse is not true. Okay. So what do we have? So we have the complex noise Vk as the sum of real and imaginary noise samples, and this is called a zero mean symmetric complex Gaussian noise. So this is, I think, straightforward because the mean is still 0. The Gaussian is symmetric and it is complex in nature. That is, it has a real part, it has a imaginary part, right? Okay. Now we saw that the VR and VI are 0 mean sigma square by 2 variance Gaussian distributed. And we saw that the expectation of Vk, which is the complex noise, is 0. Okay. What about the variance? What about the variance? So if we take the expectation of V square, then it is the, okay, so how did this come? Right, so expectation of, if we break it into a plus b square, right, a and b are the, if you consider the real and imaginary part, and if you take the magnitude of it, so if you have something like a plus ib, right, then the magnitude is root a square plus b square, right? So okay, and if you see, this will be expectation of a square plus b square plus 2ab, and this will be further expectation of a square plus expectation of b square plus 2 times expectation of a into b, but here expectation of a into b is 0. Okay, so that is why this term goes away and we don't bother about this term. So we have expectation of VR square plus expectation of VI square. And both of these variances are given to be sigma square by 2 and sigma square by 2, which we have assumed, thus giving sigma square. Therefore, my complex noise sample Vk is Gaussian 0, sigma square distributed such that its real part is 0 sigma square by 2. Its imaginary part is also 0 sigma square by 2. Okay. Any doubts till here? Okay.
Yes, sir.
Yeah.
That's all right. Sir, while the derivation is clear to me, what could you explain what exactly do we mean when we say complex noise? How do we get complex noise and how is it different from real noise?
So we generally do real analysis for ease of understanding, but in practical scenarios, the noise is always complex. Okay, so even if you consider the any modulation scheme, right? So whatever signal, so you must have heard about uh, complex baseband signal, right? It is very common term in RF communications. So the baseband signal is always represented as e to the power uh, theta, right? It is always e to the power I theta, something a e to the power I theta. So your signal is always complex in nature. So when we, what do we mean by complex is that it is having some sign component and it is having some cosine component. So so what is the basis of any signal which you transmit, right? So it is always sines and cosines, which is what the um, Fourier series tells you, that any analog signal can be represented as sum of sines and cosines. And similarly, if you are transmitting any signal over wireless communication or even wired communication, then it will always have some sine component, it will always have some cosine component, and so it will always have a complex nature, right? I hope you are able to understand. So when we say a signal is complex in nature, that means that it is having both sine term as well as cosine term. And for ease of analysis, we consider real signal analysis because it is easier for us to understand, so that we don't go into the angle of, because whenever you talk about complex, then there is always a phase associated with the complex, right? So when you have this phase associated, then it becomes a bit, the analysis becomes cumbersome. Similarly, if you remember AC analysis, alternating current analysis, which in motors and power systems. So they also consider this, you have this resistive load, inductive load and capacitive load. And you may remember that the resistive load is real, whereas the inductive and capacitive loads are imaginary in nature, right? So it is always, so whatever physical parameter we have, it is always complex in nature. And uh, for ease of understanding, we don't go into complex, but as you, so if you are currently, if you, so are you a BTech student? Uh,
Yes, sir. I'm a BTech student, sir.
Right. So if you do masters and probably into PhD, you will incur more and more complex analysis because real life things are having imaginary components, and it is necessary to understand it from that perspective, right?
Okay, sir. Thank you, sir.
Yeah. So what we saw that the, so if we consider a noise sample uh, with mean 0 and variance sigma square, then the real and imaginary parts both will have half variance. And if the actual noise sample is having 0 mean, then the then the real and imaginary parts also have 0 mean. Okay. So now what is my estimate? So my real part of estimate and imaginary part of the estimate both are having HR with sigma square by 2. And so this is very, the mathematics is similar to the previous week, right? So in previous week, what we saw that H hat is Gaussian H over and variance sigma square comma n. And we have the similar analysis, which we split into the real and imaginary parts. Okay. Now, what will be my error of estimate? So my error is represented by W. So WR represents the error in estimate in the real part. WI represents error in estimate in the imaginary part. And you have H hat R minus HR, similarly H hat I minus HI, and these are my errors. Okay. Now, again, expectation of both these random numbers is 0, right? So the errors are uncorrelated and independent, but you should note that the WR is not equal to WI, right? Because they are random variables. I mean, they can be equal, but in general, they are not equal, right? So even if X and Y are IID in nature, X is not equal to Y, right? The value of a random variable X will not be equal to random variable Y. So you should note that. So we are talking in a probabilistic sense. And when we talk in a probabilistic sense, we only want to know whether the distribution is same or not, right? And if a distribution is same, that does not guarantee that the absolute value will be same for both the random variables. So as we computed above, we'll compute the variance of error in the estimate. And variance of the error is coming to be the sum of both these complex and of the real and imaginary parts. And this is coming out to be sigma square by n. So if I summarize, we have h hat, which is the complex estimate. And it is having some mean h and some variance sigma square by n, and both of them have some real and imaginary parts. Okay. And again, if you see, this is a mean shifted Gaussian, right? So if you subtract h from this random variable h hat, the mean becomes 0, right? So in the last class, I had recommended a book. Many of you were not there at that time. So Sheldon Ross is a very good book. It is available open source, a first course in probability. The book's name, Sheldon Ross is the author. First course in probability. So you should go through this book. It is a very easy to follow book, and it has a lot of such numericals and examples to understand probability basics, right? So it will help you if you are interested to to know these things. So for instance, if I in the beginning of the class we were discussing, so h hat minus h divided by root of sigma square over n is Gaussian 0, 1, right? So why does this happen? So if you want to understand these more in detail, you should refer to this book, Sheldon Ross. Okay. So now we move towards wireless communication. So far we did not, so we were more fixed at the receiver end. And we had the signal model y is h plus v, which was only having an additive noise. So now we are going to move towards a more communication oriented analysis. So in a practical scenario, we have a transmitter, we have a receiver, right? And since the medium is wireless, and there will be some communication. So let us assume we are transmitting some X. My channel state information, this is represented by a variable H. We are receiving some Y at the receiver. Okay. So what my signal model is H times X plus V. So you should note that your transmit symbol X gets multiplied to your channel state information. So this is CSI. OK, this is CSI. And this H is called a multiplicative noise. And the V is the same V which we were dealing earlier in our previous signal model. And this is called an additive noise. Okay. So now what is unknown? So this CSI or the channel is what we have to estimate. And we will see how this estimation has to be done. So as I was explaining, we have a transmitter, we have a receiver, the medium is wireless. Now there are a few important terms which you should know. So there is something called line of sight communication. So what is line of sight communication? So when the transmitter and receiver do not have any blockages, right? There is a clear path between the transmitter and receiver in a wireless medium, then we call it to be a line of sight communication. And this channel estimate, which we want to do, the channel state information, and this channel is called a fading channel. So the wireless channel is also called a fading channel. Why is it called fading channel? Fading is a very important term in communications. We will briefly see what is fading. Since this course is not purely a wireless communication course, so I'll not go into the specifics of this, but I will try to give you a very brief overview so that you get motivated by this. OK, so what if line of sight is not available? Right? What if there is no line of sight communication, which is very common? Right? If you have outdoor communication scenario, then we usually have non-line of sight communication in that case. Right? So say, for instance, if you have a transmitter and receiver and it is blocked by, say, some trees and other buildings and other stuff. So what happens is that the your signal or your RF communication will happen by reflection, refraction, and scattering. So these phenomena help in signal propagation when you have a purely non-line of sight communication, okay, which is NLOS, non-line of sight communication. And what happens is that currently you have a single path. You have a single path between transmitter and receiver. OK, but when you have non-line of sight communication, then there is something which is called multipath. OK, so what happens is the signal travels via multiple routes to the receiver. And if none of them is the line of sight, then it is called a purely non-line of sight communication. And what happens is that there may be a possibility that, say, for instance, say you are transmitting an impulse, right? You are transmitting an impulse and you transmitted an impulse, but because there are multiple paths between transmitter and receiver, and each path has a different length, right? So say this has some distance d1, this has some distance d2, there can be another which can be having a distance d3. So what happens is that at the receiver, you observe various copies of your transmit signal, and each copy which come from a different path is differently attenuated. So it can be, so what can happen is that there's a possibility that some of the multipath is so some of the non-line of sight is better, some of the non-line of sight path is not good, right? It can happen that some path is good, some path is not good. But at the receiver, what you see is that and they will all come at different delays, right? So if you have the time scale, you see that some so all these impulses are the copies of what you transmitted, and say some came at T1, some came at T2, some came at T3, and there can be a possibility that these symbols which you are receiving may overlap with each other. Right, they may overlap with each other, and that leads to inter-symbol interference, ISI. So when you have line of sight communication, when you have a purely line of sight communication, there is no ISI. Okay, when you have a pure line of sight communication, there is no ISI. But when your communication is not purely line of sight, in that scenario, we have multiple paths from where your signal can reach the receiver, and this leads to multiple paths, which leads to inter-symbol interference. So this we will discuss in week 5, 6, 7 as we process through the course, and we will see how this inter-symbol interference can be negated, and that is a different analysis. There can also be a scenario where you have both line of sight and non-line of sight communication. This is also a very interesting scenario. That is, you have some that while you have a line of sight, but still because you have say you have outdoor scenario, so you can have like there is some reflection or some scattering happening, and due to which there are some non-line of sight components also, right? And this may also lead to ISI. So utilizing this multipath at the receiver, this is called time diversity. This is called time diversity. That is, you want to so different paths are giving you different samples of the same signal which you are transmitting, right? So you are receiving different copies, some of them, and each of them will have different attenuation, right? So this will have some channel H1, this will have some channel H2, this will have some channel H3, and each of and your signal will be attenuated differently in each of the multiple paths, and when it comes at the receiver, and then that receiver processing is called time diversity analysis. This is also a separate topic, but I'm just trying to motivate you towards wireless communications so that you get a flavor of the subject. Okay. So now what are some fading models? So which we consider. So you must have possibly heard of this distribution. This is called a Riccian distribution. This is a so we normally study Gaussian distribution, right? But there are some other PDFs also which are very common in wireless communication sense. So I just wanted to share these details with you, but they are it is not related to the current course. Okay, so you don't need to bother. So just you can know possibly that if you have a purely line of sight communication, then the signal which is received at the receiver will have Riccian fading. Okay, and similarly, when you have a purely non-line of sight communication, then the signal which is received has Rayleigh distribution. So, okay, and what is fading itself? So it is a variation of received power at the receiver due to multipath. Okay. So a few again two reference which I wanted to share with you. So this is a very good book for beginners by Rappaport, T.S. Rappaport, named Wireless Communication Principles and Practice. So you can refer to this book to know the basics of wireless communication. There's another very good book which we study in PhD coursework. This is book by Andrea Goldsmith. This is a Cambridge publications. It's a very good book. And if you want to go into a bit mathematics of wireless communications, then this is a very good book. Okay, so anyways, for this NPTEL course, you don't need to bother so much. Okay, right. So now we consider a purely line of sight scenario. So we for our analysis, current analysis, we consider a purely line of sight scenario. So you have a transmitter, you have a receiver, you have the CSI channel side information, which is denoted as H, which is also called the channel gain. Okay, and you have and you are transmitting some symbol XK and you are receiving some symbol YK. Okay, and this is your signal model. YK is H times XK plus VK. So what will happen is, so if you see this scenario, so if you subtract YK minus H times XK, you get VK itself, right? And what is VK? VK is Gaussian 0, comma sigma square. So if you see Y minus X into H is having this distribution Gaussian 0, comma sigma square, right? So what will happen? So YK. So if you add this term H times XK to the mean H times XK, comma sigma square. So if you see, your VK was a Gaussian 0, comma sigma square, right? And if you shift this mean by H times X, then you receive Y. Okay, so it is a mean shifted Gaussian. Your received symbol is a mean shifted Gaussian. Okay, and this PDF f of yk is given in as in this equation. So 1 over root 2 pi sigma square exponential minus yk minus h of xk. This is your mean. It is squared over 2 sigma square. Okay. So this is for one time instant. So what will we do if we have multiple time instants? Then we need to find the joint PDF over multiple time instants. Okay. So consider you have this vector y, which is storing all the observations y1 to yn, and we want to find this joint PDF. So this joint PDF, because now we again remember the IID property, which we discussed above, identical and independence property, and by which property is individual product equal to multiplication, individual product equal the joint PDF. This is the independence property. Okay. So by independence property, the joint PDF is product of individual PDFs, and this is your individual PDF, right? This equation. This is your individual PDF, and for n samples, if you multiply the same PDF, so the scalar term 1 by root 2 pi sigma square to the power n and exponential minus 1 over 2 sigma square, and now we have a summation inside the exponential and y minus h of xk whole square. And this summation moves from k is 1 to n. So what is unknown? We know x, right? What we are transmitting, we know x. We know y. What we are observing, we know y also. Okay. We know sigma square also. We know how many samples we have sampled. So we know the value of n. We know n also. What is unknown is h. That is how my channel is behaving. That is what we need to find out. Okay. And for this problem, we assume that the channel does not vary over these n time instants. Okay. We assume for simplicity that our channel is not varying over this n time instants which we have sampled. Okay. So we take a log likelihood to find out this estimate. So as in week 1, we are again doing the maximum log likelihood estimator. Right. So this estimator is what we are again using the same concept. So we take the logarithm of the likelihood. Okay, so this equation is the likelihood equation. And we discussed in the last class that by Bayes rule, we have the a posterior is likelihood times prior, right? So if I write it mathematically, your probability H given Y is probability Y given H into P of H divided by P of Y. Right? This is your Bayes rule. And since my H is non-deterministic, okay, so we don't bother P of H. P of Y is more of a normalization. Uh, it is more of a normalization constant. You can assume it, right? So your a posterior and likelihood. So maximizing the a posterior is equivalent to maximizing likelihood for this case, which we are currently considering. So we want to maximize the log of the likelihood. Okay, so if you take the logarithm of this function of this likelihood function, then you get minus n by 2 natural log of 2 pi sigma square minus 1 by 2 sigma square summation yk minus h xk whole square. And since we want to find h, so we differentiate with respect to h and we equate it to 0. And if you solve it, you will get that can you please mute? Okay, thanks. So we have this h hat is summation k is 1 to n xk yk over summation x square. Right? Any doubts up to here? Okay. So this is the maximum likelihood estimate of my channel. Now, if you take this from a vector perspective, so this is currently in a scalar perspective. So if you take it from a vector perspective, then you have say my x vector, which is my transmit pilot vector, right? This is the vector which I am transmitting from my transmitter, and this is represented as x1 to xn. What we are observing is say y1 to yn, and so x transpose y, right? What is x transpose y? So you have x1 to xn, and here you have y1 to yn, right? This is x transpose y. Try to understand. So each element of x is multiplied with its corresponding element in y vector, and they are consecutively added. Right? So this is called x transpose y. Similarly, what will be x transpose x? So you have this vector, x vector. You take its transpose, so you have a row vector and you have a column vector. Right? And so now what will happen? You will have x1 square plus x2 square plus so on xn squared. Okay, which is summation x k squared. Right? Okay. So this estimate in vector sense, you can denote it as x transpose y divided by x transpose x. Right? Okay. And if my channel is complex in nature, then what happens is that this transpose now becomes the Hermitian, which is this is the Hermitian operator. which is conjugate transpose. So you take the conjugate of a vector, of a complex vector, and you transpose it. Okay. Also, this x transpose x, which is x1 squared plus x2 squared and so on up to xn square. This is also mathematically called the L2 norm squared. That is the square of the L2 norm. So in mathematical language, you have L1 norm, L2 norm, so on, L infinity norm, right? So you have various norms in mathematics when you have a vector and you can perform many operations on the matrix, right? So there are various norm which we can compute, and this norm, so the definition of L2 norm is this under root x1 square plus x2 square so on up to xn square, and if you square the L2 norm, then you get this. So this is just for general information I wanted to share. So what do we have now? If we consider a multi-time instant model, so remember we still have single transmit antenna and single receive antenna. Okay, so we still have a single transmit antenna and we have a single receive antenna. They are still 1, 1. Okay, and if you observe over multiple time instants, these are over multiple time instants. So y1 up to yn is the vector which you receive at the receiver. H is my channel state, which is assumed not to change over these n time instants. X1 to xn is the pilot which we are transmitting, and v1 to vn is the additive noise samples. Okay. And again, we have the old assumption that is all VKs are IID and they have 0 sigma square Gaussian distributed. So what will happen is, since each VK is IID distributed, the expectation of all VK is 0. Okay. Expectation of V square K is sigma square. Now you will ask how this came. So what is variance of any random variable? So it is the second moment minus first moment squared. Okay, what is second moment? So you have expectation of v square minus expectation of v whole square, and since here expectation of v is 0, so this second term becomes 0. So you have variance is expectation of v square. Okay. The expectation of v square is sigma square, which is variance which is given, and expectation of two samples of v is 0. That is, all the v's are uncorrelated with each other. Okay, they are all uncorrelated with each other. And this correlation matrix, so if we represent this correlation in terms of a matrix RV, that is expectation of VB transpose. So what you see is you have expectation of V1 square, V1, V2, so on, V1, Vn. Similarly, Vn, V1, so on, Vn squared. So you get a diagonal matrix, and all the diagonal elements have value sigma square. And this is your correlation matrix. Okay. Now, so we have y is h times x plus v, which is my signal model. H hat is x transpose y over norm of x square. We derived this above. So if this y is broken as x times h plus v, which was the definition of my signal model, then what we see, and now if you multiply, if you solve this, right, so you will get x times So you will get this plus this. And what is x times x? This is the denominator itself. So they both cancel out each other. So what you are left is h hat is h plus this term. Okay. Now, if you take the expectation of this equation, so you will have expectation of h plus since x and norm of x squares are scalars, so expectation operator goes inside, and v is my only random variable here, right? So expectation always works on the random variables, and the scalars are outside the expectation. This is again a property, and expectation of v is 0. So the second term cancels out, and what we get is expectation of h hat is h itself, which is a unbiased estimate. Okay. Similarly, if you compute the error now, what is my error? So my error is h hat minus h. Okay, h hat minus h, and this is x transpose v over norm of x squared. And if you want to solve the variance of this error, then it is defined as expectation of h hat minus h transpose. And this we got this term, right? So this term into the transpose of this term. And so now the denominators come out, which is 1 by norm of x to the power 4. And this, so A into B transpose is B transpose A transpose. This is a property, okay, of matrix. So what will happen? This comes here, x transpose B, B transpose X. So there's another property, transpose of a transpose is the matrix itself. Okay. So that is why you have this X. So X transpose of transpose is X. And as I said, expectation works only on the random variable, so the scalars will come out. So what will happen is you have expectation of VB transpose, which is sigma square times. So this we saw about it. So you have this diagonal matrix having sigma square all around. So this can be sigma square if you take common, and you are left with a identity matrix. Okay. And if you solve this, you have sigma square, and x transpose x is again, this is norm of x squared. And so the numerator and denominator will cancel out for the terms, and you have sigma square over norm of x squared. Okay. So for a complex channel, if I finish the analysis, so since we had here x transpose y, right, and this will be, oh sorry, this will be x Hermitian y over x Hermitian x. Okay. And your variance becomes, so this norm, which was x transpose x for real case, it is x Hermitian x for complex case. Okay. And the variance of real part equals variance of imaginary part, which is sigma square by 2 norm of x whole square. Okay. And you should note that the estimation errors of the real and imaginary parts are uncorrelated. So a very quick final summary. So for a signal model y is h plus v, we have the estimate h hat, which is Gaussian distributed having mean h, and variance x transpose y over x transpose x, and the estimate of variance of the estimate, error in estimate, is sigma square over x transpose x. Okay. And if you have complex, then you have Hermitians, which Hermitian operator instead of the transpose operator. So any doubts up to here? I'll now proceed to the problem solving. So you can ask. Yeah, someone has raised hand. You can talk. Someone has raised his hand. You can talk.
Sir, my name is Manish. I have some query.
Yeah.
Yes, sir. What is the exactly difference between Hermitian or norms? Is it any relation or not?
No, so norm operator. So if you have a vector, right? You have x vector, x1 to. So is my screen visible, right?
Yes, sir.
Okay. So you have say some elements x1 to xn, and if you take the norm of it, right? So norm is, and if I talk about L2 norm, then it is root of x1 square plus x2 square
Sir,
plus xn
it's not
square.
visible. Sir, it's not visible.
Screen not visible?
Yes, sir.
Okay,
It is visible.
Elias sir, can you log out and again log in?
Yes, sir. Yes, sir, it is visible, but only the norm, what I have written, till that area only it was visible.
Okay.
After that,
okay, let me check from my end. Okay, just check. Okay, I'll share again. Just share screen. Just a minute. Is it visible now? Hopefully. Is it visible?
Yes, yes. Now visible.
yes, sir.
Okay. Yeah. So for any so this is a column vector, right? So if you want to take its L2 norm, then it is the root. You take the root of summation of all squares. Okay, this is the definition of norm. And I think you're confusing with Hermitian, right? Hermitian operator. So what will be X Hermitian? So X Hermitian will be conjugate and transpose. So it has nothing to do with summing and squaring and rooting. OK, so if you have. So if you have, say, a plus ib, c plus id, x plus iy, this is my initial operator, right? So my Hermitian will be a minus ib, c minus id, so on, x minus iy. Right? Are you able to understand?
Yes, sir.
So,
yes.
Right. So this matrix which you get is the Hermitian matrix. Okay. Any other question?
Okay, sir. Thank you, sir.
Yeah. All right. So we'll proceed to solving some problems of week 2. Is the screen visible again?
Yes, sir.
So for week 2, so these are previous year numericals which we'll be solving. Okay. So what we have is we have a signal model y is h plus v. We have n samples and the noise is now Bernoulli distributed. Okay. Such that probability that it is Bernoulli distributed with 1 is p and probability that is 0 is 1 minus p. And what is expectation of h hat minus h square? That is variance of the error estimate. Okay. And it is given in the question that the estimate is minima of yk. Actually, this previous part of this question was solved in week 1. So if you will check the video of last class, so week 1, I think question 10, right? So week 1 question 10 was its first part where we derived this minima of yk. So you can check that video, right? And this is the second part of that question, which has come in week 2. Okay. So we have y is h plus vk. Okay. Yk. And vk is 0 or 1. This has a probability of 1 minus p, and this has a probability of p. Okay. So and it is given that h hat is minima of yk. So see what will happen is that this h hat will have two scenarios. So h hat will be h for all scenarios except when all vk is 1. Okay, so try to understand. If you have some samples, say you have n samples and your noise is having some zeros and some ones, right? So the minima will always be h, right? So it will be h comma h plus 1 comma h comma h plus 1, and you will have such a set. And if you take the minima of that set, it will always be h, right? Because h is always lower than h plus 1. In the second scenario, h hat will be h plus 1 only when all vk is 1. Now in this case, you will all the samples will be h plus 1, h plus 1, h plus 1. And so the minima of h plus 1 will be h plus 1 itself. OK. So what is my error? So h hat minus h is 0 for case 1. It is 1 for case 2. OK. And if I take the expectation of square of this error, right? Expectation of h hat minus h squared, this will be 0 times 1 minus p to the power n plus 1 times p to the power n, which is p to the power n. Okay. And go ahead. Now we have signal model y is x times h plus v. So the signal model has changed. You have n number of observations. The noise samples are given IID, 0 mean Gaussian. What is the likelihood? So we derived this, right? So this is a scenario when you have this transmitter, you have the receiver, right? You're transmitting some x, you are receiving some y. This is h. So probability of y vector given h. So this is 1 by under root 2 pi sigma square to the power n exponential minus 1 over 2 sigma square summation k is 1 to n and yk minus what is the mean h times xk squared, right? So this is what is your likelihood, which is option D. Okay. Now consider a fading channel estimation problem where the output y is h x plus v, and we have some pilot vector x, we have some y. So what is the ML estimate of h hat? So we derived this, right, that h hat is Gaussian with h X transpose Y over X transpose X. Oh, sorry. So what we saw that H hat is X transpose Y over X transpose X, which is this is the norm square, right? The denominator. And we saw that H hat is Gaussian H sigma square over X transpose X. Right. So in this question we are asked the estimate. So estimate is X transpose Y over X transpose X. Now we are again given the same signal model Hx plus V. The variance of the estimate. So we just wrote above H hat is Gaussian distributed H sigma square over X transpose X. This X transpose X is nothing but the 2 norm squared. Okay. So option D. Okay. Now we are given some values of X vector. We are given some values of Y vector. We are given sigma square is 6 dB. What is the ML estimate of H? So what is H hat? It is X transpose Y over X transpose X. So here if you see all are real numbers, right? So this is a real analysis. It is not a complex analysis. Okay. Now since it is a real analysis, so what will be X transpose Y? So -2, 1, 3, -3. Similarly into 3, -1, 2, -1. So this comes out to be -6, -1, 6, 3 is 2. Okay. And X transpose X. So for X transpose X, you need to square all the terms, right? So you have -2 squared, 1 squared, 3 squared, -3 squared. So you have 4, 1, 9, 9, which is 23. So you have 2 over 23. Okay. Next question, you have the same question and you are asked the variance. Right? What is the variance? So first, you should note that here sigma square is given in dB. So we need to convert it to watt. Okay, dB has to be converted to watt. So 10 log 10 sigma square is 6. Okay, so sigma square in watt will be 10 to the power 6 by 10. And this is approximately 4. Okay, if you solve it by calculator, you can use a calculator. So what will happen is that and we had computed X transpose X above, right? This is 23. So what is my variance of H hat, which is sigma square over X transpose X. So this is 4 over 23. Okay. Next question. You are again given X. You are again given some Y. You are given sigma square. Okay. So this is again similar question of the unit Gaussian conversion, right? So just remember H hat is Gaussian H sigma square over X transpose X. Okay, and we need to convert it to and what do we need? So probability that -1 by 4 H hat minus H 1 by 4. Okay, this is what we need, right? So what is the first step? So since it is H hat minus H, so H hat minus H is a zero mean Gaussian, right? So my mean term is gone and I am left with the variance term. How to remove variance? So to remove the variance, I will be dividing with root of variance, which is the standard deviation. right? And this random variable is Gaussian 0, comma. So if we do that, so here we have probability -1/4. And what is this root of this variance? So if you remember that we compute variance in this problem, right? So variance is 4/23. So we need to divide by root of 4/23. Right? So you will be dividing by root of 4/23. What is root of 4/23? So you have root 23 goes to the numerator if you divide, right? And root of 4 is 2. If anyone feels that they don't understand, they can stop me, right? Okay. And here you have h hat minus h over root of sigma square over x transpose x. This is 1/4 root 23 2. Okay. This is q of minus sorry. No, it was correct. So q of this by 8 minus q of root 23 by 8. This is 1 minus 2 times q of root 23 by 8. So here in the option, it is in denominator is giving root of 64, right? So the root of 64 is nothing but 8. So this you can write as root of 64, right? So is this question clear? Okay. Next question. So now we are given a complex channel coefficient. Okay. So far we were doing a real analysis, and now we are. Yes.
Sir, in question number 3, I think.
Okay.
Can you go to that, sir?
Just a minute. 3. Okay.
Yes, sir. Here.
Okay.
In the problem, the numerals is given, right? Next.
Okay. Next question. Okay. Yeah.
Yeah. Here, yes, sir. Here the y is given like 3 -1 2 -1 transfers, right, sir?
Right.
X inverse y. That y cannot be taken like 3 -1 2 -1, right, sir? It is already given as transfers.
Okay. Let me just. So there is this. See.
I think the problem.
Yeah. I got it. I got your point. So x transpose of y is y transpose of x. Okay. So what will happen is, okay, let me do it by that way. So
Yes.
we have to do x transpose of y. Okay. So just a minute. So x will be a row vector, right? So you have -2, 1, 3, -3, and y will be a column vector, right? 3, -1, 2, -1. So it is the actually it's the same thing because both are a row vector and a column vector. So you multiply it in any ways. So you are going to get a scalar, right? So you will be getting a 1 cross 1 element at the end. So what we will have is again same thing, right? So -2 and 3 will get multiplied. You will have 6. 1 minus 1 is -1.
Sorry to interrupt. My doubt is y is given like transfers, right, sir? 3 -1 2 -1 transfers.
Right.
So the if you are taking that y as it is, then it's supposed to be taken like column vector, right, sir? Not
Yeah.
in the.
So here, can you see this in the right hand corner which I am solving? Can you see
Yes,
this?
sir.
Right. So here I have taken y as a column vector, right? 3 -1,
Okay.
2 -1.
Okay.
You can
Then
see this,
again,
right? Yeah. No, just a minute. So here, if you multiply, so this is what we are doing, x transpose y. Okay, this is
yes,
x
sir.
transpose y. So what will you get? -6, right? -1 plus 6 plus 3. Okay. So that's the same thing we got above also. Can you see? So that is what I was trying to say, that since here you have a single row vector and a single column vector, X transpose Y and Y transpose X are same actually.
Same. Okay, sir.
So what you get is 2 only. Similarly, when you do X transpose of X, so what will you get? Let me just do it. So so similarly, X transpose X is X transpose. Okay. So what will happen is X transpose will be a row vector. Okay. So X transpose will be -2, 1, 3, -3, and you will have a column vector -2, 1, 3, -3. Right, sir? So when you multiply, anyways, you will get the same thing. -2 into -2, which is -2 squared.
Yes, sir.
Right? 1 into 1 is 1 squared. Similarly, 3 squared, and you have -3 squared. So it's the same thing, right? So you get 23 only. Okay.
Yes, sir.
Anyways you do. Right.
Thank you.
So right. Okay. Okay. So what we have is the variance is now given as -3 dB. Okay. So we need to find the ML estimate of H. What is ML estimate of H? Since it is complex, right? So this is X Hermitian Y over X Hermitian X. Okay, this is the formula. So let us first do X Hermitian. Okay, X Hermitian will be, it will be a row vector. Okay, 1 plus 2j minus 2 minus 3j, 2 and 3 plus j. Okay, and so X Hermitian into X. So 1 plus 2j minus 2 minus 3j, 2, 3 plus j, and you multiply it with X, which is 1 minus 2j. Okay, minus 2 plus 3j, 2, 3 minus j. So if you solve it, you have 1 minus 4j square plus 4 minus 9j square plus 4 plus 9 minus j square. So you will get 1 plus 4 plus 4 plus 9 plus 4 plus 9 plus 1. So you should note that j square is -1. Okay. And this will come out to be 32. Similarly, this is the denominator. Okay, this is the denominator. Similarly, for the numerator, X Hermitian phi. So if you do X Hermitian, which is again 1 plus 2j minus 2 minus 3j, 2, 3 plus j times y. What is y? J, 1 plus j, 2 minus 2j minus 3 plus 2j. Okay, and if you solve it, you will be getting, yeah, minus 8 minus 5j. Okay, so you can do this. It's a very simple calculation actually. So numerator over denominator. So -8 minus 5j divided by 32, which is your denominator, right? So you have -1 by 4 minus 5 by 32. Okay. Now, what is the variance of this estimate? So just to remind that here, okay, what is the variance formula? It is sigma square over X Hermitian X. Okay, and X Hermitian X we computed as 32. Okay, in the previous question. So this is 32. And again, note sigma square is -3 dB. So you will convert 10 log 10 sigma square in what is -3 dB. So sigma square in watt is 10 to the power minus 3 by 10. And this value actually comes out to be around half. You can use calculator for that. So the variance will be 1 by 2 into 32, which is 1 by 64. Okay. Finally, this is again the same question. You have x, you have some y, sigma square is given minus 3 dB. What is the variance of real and imaginary parts, right? So variance of so the variance of complex part. So if you remember, it was sigma squared, right? And the variance of the real part and the variance of the imaginary part. So they were sigma square by 2, sigma square by 2. Okay, so this is what in the analysis which we saw earlier. So since variance of C is 1 by 64, which we just computed here. So it's an extension of this problem. So 1 by 64 and half of 1 by 64, which is 1 over 128. Okay. So any doubts? Any doubts?
Yes.
Yeah, please
Is
ask.
it possible to share this notepad or this PDF document?
Yeah, we can share that. So what I'll do is after this class, I will share it in the Google group which we have, right? So I'll put
I
in
am
there.
not part of that Google group right now.
So have you not registered for the course, madam?
No, I have registered for the course. We are getting emails on our Gmail as well.
No, that is fine. If you log into the Swayam portal, right,
Yeah.
the Swayam NPTEL portal,
Correct.
and then you can go to your course, right? If you go to this course, there will be an option, ask a question.
Yes,
There
yes,
will
correct.
be right. If you click that, this Google group will open automatically, and you can also see what question others are asking. And I will be putting this video YouTube link on that. I'll share it there.
Okay, that would be helpful.
Yeah. So I shared for previous week also. So for this week also, I'll just put there so you can see the video again if you want.
Yeah. Okay. Thank you very much.
Yeah. Okay. So if there are no other questions, then I'll stop recording. Okay. Thanks.